Welcome back to Ye Old Foundry, ladies and gentlemen. Now, as inadequate as it may be, I'm going to try and teach how the Navy molders repaired Babbitt bearings. Okay. I still feel real disappointed that I couldn't get my hands on a bearing to do it with. Perhaps in the future I'll be able to. Okay. And if I am able to get my hands on it, then you'll be able to use the video that I'm making here to compare the step-by-step that I take. Okay. So I'm going to yeah, there it is. Got to make sure everything's here. I'm doing kind of strange here. I have got this paired with my iPhone. First time in 40 some odd videos. I had to in all the other videos I had to kind of guess, you know, that you were able to see me. And at least looking at the feedback over to my right here, I'm able to see if I'm in the shot. If for instance, if I had over at my window over here, I had too much glaring daylight coming in that made it look bad, which it did, to see if the white, pardon me, if the whiteboard was positioned good enough for me to use without it. I mean, there were times in the past where it really wasn't good looking. I mean, you know, you couldn't see nearly as well. Now, my camera is 1.5 feet, 2 feet away from this whiteboard, and look how far it looks like it's there. Okay. Well, I'm using, as I said, my iPhone to display what's in the shot, but having the iPhone in the shot, you're going to hear noises coming from it, from the different you know, people trying to send me messages. So those are going to be what the weird noises are. Okay, but so let's start. Okay, now this isn't going to be a short video, or if it is a short video, it's going to be because I divvied it up into different segments. The first one, where I went through the historical, you know, stuff to try and explain what the Babbitts were all about, that would be part A. Okay. This is likely to be part B. I hope it's part B, because this is the next part. So, what are we doing? Okay, we're setting up a scenario. The scenario is that you're a worker in a foundry, and somebody has delivered a couple of bearing shells to you. These bearing shells go on a shaft. They support a shaft in a mechanism, and what you got to do, you have to do, your job is going to be to take out all the old bearing material, all the old Babbitt, and then put in new Babbitt, and then send the bearing shells, you know, after you clean them up a bit, down to the machine shop and let them finish the rest of the process. Well, you're going to be doing it the same way in your shop. You know, if you're a machinist, great, because you'll have everything you need to do the machining and the boring. Okay? Because when I say that, is that there is going to be some machining involved at the end of this, despite the fact that you could cast this around the shaft that you have. You know how you can smoke the shaft, put a layer of carbon around the shaft, by putting it through oxyacetylene, smoke, or over a smoky fire, with a bunch of smoke coming off of it. You could go ahead and cast it around that. But the problem is with doing that is that if you leave it that way, you're not going to give it enough of a gap in between the Babbitt material and the moving shaft to allow oil to be down there. So you're still, even if you cast it, you're still going to have to take those bearing shells, the two halves, the upper and lower half, and put it through a machining process to give yourself, I don't even have the paper with me, but you'll have to find out how big of a gap you need in there. And it wasn't very big. It was like 10 thousandths or something, just enough for you to be able to have a standing pool of oil down there to act as a not only a lubricant but as a support for that portion of the shaft. Keeping in mind that the bearings, Babbitt bearings, were designed to take advantage of the fluid dynamics law that the liquids, well, they're not incompressible, because I have no doubt that you can compress it some, but under normal circumstances, without giant machines or anything like that being attached to it, liquids are incompressible. So they will act as a surface on which the shaft will ride as long as you have a layer of oil in there. Okay? So, here we go. Number one, melt out the old Babbitt. Okay? You got various sources of heat that can be used, like a hawk burner. Oh, and incidentally, I am going to be putting some pictures in this so that you guys, they can illustrate what I'm talking about. Like a hawk burner is what we used for larger bearings in the foundry on board the ship. Okay, and the best way to describe it, a hawk burner is let's say a cylindrical canister of diesel fuel, about 10 gallons, 15 gallons of it, and it sits upright. You connect your air hose to it, and you connect a flame source to it, and once you've pressurized the where the fuel is, the canister, then it shoves the fuel through the it looks like a flamethrower. Okay, if you ever watch any of the World War II shows, like on Iwo Jima or any of those places where they used flamethrowers, it looks like you're holding a flamethrower, with only a little exceptions of the shape of it. Okay, basically you would just once you got everything pressurized, you got your hoses hooked up to the canister to allow the pressurized fuel to go to the burning portion of it, the flamethrower portion of it. You turn on, or you open the valve that lets the fuel out, and what you have is a cloud of vaporized or atomized diesel fuel that's able to be lit fairly easily. Okay, and once you light it, whether it be you light it by way of aiming the fuel source onto a burning rag, or you already have a oxyacetylene torch hooked up and you use that to start it off, you light off the air fuel mixture, and you start melting out the Babbitt, or rather you heat up the bearing shell that the Babbitt's in, and you bring it up to the temperature so that you see the stuff melting out, pouring, starting to drip out. Okay, you can do it. You know, you do it that way with. You can use a hawk burner, as I said before. You can use it. Use an oxyacetylene torch that has a large tip. You don't want a tiny little tip because you don't want to concentrate the heat onto small areas of the bearing shell, thereby either melting those small areas or warping the bearing shell because you've heated up a small area a lot and the rest of it hasn't really been heating up much. And or you can put it in an oven. Ovens, I would vote for oven because you can set up the temperature, which is about 900 degrees Fahrenheit. You turn on the oven at set it up to 900 degrees Fahrenheit. You put the bearing in there, bearing shell in there. Well, it's a bearing still. It's not a good bearing, but you put the bearing in there and you check on it ever so often. Once it gets up to 900 degrees, you open up the oven, you look in there, and you can leave it inside the oven and brush it clean. Okay. Now keep in mind. Always keep in mind that the process is requiring you to do almost like with the wire rope sockets. Once you clean the part that's got to be clean on the bearing shell, which is the inside curvature and the edges, you can't get anything on that. Okay, so everything you use touching that after the Babbitt is melted out, it's got to be clean. And normally you're not going to want to use much else other than a wire brush. All right, because that can handle the heat. Remember, this is going to be almost 1,000 degrees. So you're going to have gloves on. You're going to have to use something that's not going to catch fire or melt or anything like that while you're trying to work with the inside of this bearing shell. So it's got to be a stainless steel, well, it's got to be a wire brush, and it's got to be clean. It's brand spanking new, no oil on it at all. If you try, wipe anything that has oil film on it or is dirty, you just, now you got to go through a whole new process of degreasing it and cleaning it that way, because remember, you just heat it up again. That's not going to get rid of it, because even if it does dry it out, whatever grease that might be there, you're still going to have the ash associated with that burnt up grease sitting on the inside of what's supposed to be a nice clean bearing shell. Okay, so using a clean wire brush, brush all the molten metal from the surface of the bearing shell. Then wipe with a dry and, dare I say, clean cotton cloth. Now, because of its high heat, your cotton cloth will not burst into flame or melt against the hot metal. It'll char. It'll get a little bit carbony. But that's not going to, it's going to stay on the cloth, okay? And besides, you're going to be, most of this stuff just melts off and falls into, let's say you have a tray underneath it. It's going to fall into a tray. Let me go ahead and move this back here. It's going to fall into a tray that you have underneath it so that it doesn't just fall to the bottom of your oven. And that's the majority of it. Now you're taking a wire brush, you're you're moving it all up and down, you're rubbing it on the inside of the curvature. You're gonna make sure it gets down deep inside any dovetail, machined dovetails that might be inside the inside curvature of this bearing shell, or if there's any anchors that have been drilled in there. You don't see that so much anymore, because a great deal of the people, a lot of the people, let me put it that way, a lot of the people who actually have to do this work anymore realize that all they have to do is just really clean the inside of the bearing shell, tin it properly, and the Babbitt material will automatically adhere to that surface, okay, without hardly any effort. All you got to do is just pour it into the mandrel, and that Babbitt material, being as hot as it's going to be, will melt and adhere to the tin, which is bonded to the bearing shell, okay? To make the whole process really, really quick, that's basically what's going to happen. But you can't do any of that if it's dirty, all right? So let's say you've melted out the majority of it, you've wire brushed the stuff, the rest of it, but you still have a little bit of a film in there. So you take your wadded up cotton, clean cotton rag, dry. We don't want a cooling effect from the water, because it's going to turn into steam, and the steam is going to take away the heat. And you want this stuff wiped quickly before whatever's left in there solidifies. All right. Otherwise, if you do that, you're just going to have to heat it up again and get rid of the rest of it, because where that solidified Babbitt is has frozen to, you're supposed to put tin there, okay, as the interface material. Excuse me. For the Babbitt to adhere to, okay? So take a dry rag and wipe it quickly, and that should remove any hanger-ons, little bits of Babbitt that might still be on the inside shell, okay? Then you just let it go and cool down at that point, because now you've got to set up preparing that bearing shell for tinning, okay? Now, what that entails is that what you have to do is you have to thoroughly clean, whether it be by physical means, whether it be by chemical means. You've got to physically clean the places where the Babbitt's going to be cast, okay? And what you're really working on is you're trying to get rid of any oxides that might have formed over time on the inside of the shell. And you're going to get, and this is not quite as often, it's just strange. Once in a while it'll happen. But in the process of actually manufacturing the bearing shell, if they didn't do the best job at the steel plant of casting this, they might have had a deposit of oxides or carbides, throughout the mix. And, slag might have gotten into the mix and got shoved down or poured down into the mold where the bearing shell was cast. You run into that, and it looks like a surface of a defect, because what they're doing when they make that bearing shell is that they not only cast it, they clean it up, they clean up all the edges on it, they take it down to the machine shop machines out the inside, so the machine, or rather the inside curvature, is going to be as smooth as possible. I've seen some like almost mirror smooth, but not quite that smooth, because they do have to have a place on that surface for the tin to grip more mechanically than chemically. You want to add that to it to just help the process along. Okay, so when they machine out the inside of that bearing shell, they give it back. They give it to whomever's got to put the Babbitt in it, and that's brand new, and it's still going to be oily, because the machine shop many times uses a coolant, and some of the coolants are oil-based coolants. So the inside of that bearing shell has still got to be cleaned before it gets tinned, okay? Now, there's several different ways that the bearing shell can be cleaned or prepared for tinning. Okay. First, I already explained about the oxides. You could coat the inside of the bearing shell and the outside edges, okay, with a zinc chloride or salmoniac flux, okay. Excuse me. If you, you'll find when you start heating that bearing shell back up, getting ready for the tin, if you don't have a flux that you can slather on there, like a paste, kind of like the fluxes that are used by pipe fitters to clean their joints and before they braze them up. If you got that kind, you can wipe that all over, and that'll stay in place and melt as you heat the bearing shell up, getting ready for tinning, okay? Sometimes, though, like we didn't have the kind that you brushed on. We had a container of powder granules, really granules, almost like salt. And whenever we were, trying to apply the tin, if we came to an area that was a little more stubborn and almost refused to easily allow the tin to be put in there, we would take a pinch of that stuff and sprinkle it on there, because don't forget that bearing shell is still real hot. So the flux melts right away, combines with the oxides and floats the oxides away and cleans that up, and you're able to get in there with a tin, however, well, in this case, this scenario, it's going to be a tin stick. You rub it in there and it adheres right away, okay? And you go from one side to the other so that it, once you get from this side to the other, everything is still a little bit hot. And if you've got a real good tinning, you could take the bearing shell and you'll have a wet mass of, a molten mass of tin in there. You go with your lots of gloves, okay? Heat-resistant gloves like welders' gloves, or if you can get your hands on foundry gloves, that'd be even better, because they got a lot more thermal insulation in the palm. You can move it back and forth, and it'll almost look like you have a wave of tin flowing across it. That's beautiful. That means every bit on the inside curvature has been covered by tin. All right, now I'm going to put a drawing up here. Now it's not. I'm not a good hand, manual drawer. So I'm gonna, just to illustrate what this is, what I'm going to be trying to do here for tinning. I jumped over something. I don't want to. I want to keep this. I've got my little script here. Okay, got my little script here, and I'm going to try and make sure that I stay step by step by step. You have just used flux for tinning, right? Okay, so let's say you don't have a flux right now. Well, in order for you to try and tin it without a flux, you can put the inside of a bearing, rather that bearing shell that's you've just wiped all the old stuff out. After it's cooled down, put it in a sandblaster. Sandblast all the portions of the bearing shell that you have to tin. That's another way of getting the oxides off of the surface of the steel. Now, it could be steel, could be cast iron. I've even poured bronze bearing shells. I mean, that was like decades ago, but, and maybe only a couple of them in my earliest days in the foundry, because it wasn't very often after that you ever saw bronze bearing shells. The bad news about sandblasting, even though you're absolutely going to get all the oxides off of there, now you got to get all that fine dust off of there. What we used to wipe those clean is not water, because if you put water in there and there's any time between the time you start and the time you're starting to heat it up to tin it, you might be introducing some rust in there. Okay, you don't want anything to any kind of oxides to grow in there. That's what oxides are. Remember, rust of the type, whatever type of material you're using. In this case, it'd be iron oxide, but you don't want any of that to be formed because it's you know, you don't always get these done on the same day. So instead of using water to try and wipe those places clean from the dust that you accumulated from the sandblaster, vinegar. Get vinegar. It doesn't make any difference what it is. It's still going to be a liquid that you're going to be able to get on a rag, and you're still going to be able to force that dust off the surface using that liquid. Okay, so could just clean it well before it gets, it gets dirty again. Okay, you could also pickle. Put it through a pickle. This is a process that some of the people used, and don't forget when I say some of the people being mechanics. It made a difference whether you were an auto mechanic, whether you were a electrical mechanic, because you might be in charge of electrical switching devices and stuff. Some of the big stuff had bearings in it. So, it could be any place that, some of the big mechanical kind of jobs where you have to replace a bearing. Now, in this case, you could go ahead and get the bearing shell all wiped out from the old bearing material. Now, these people that I'm about to this is another way of cleaning the bearing shell. You dip it in a pickling solution. Okay, you're going to acid etch it, in other words. All right, so let me hold on a second. I've got to check on something. It looks like the device has, I don't know, maybe I'm running low on power. All right, I'll be right back. All right, welcome back. I don't know why this thing said we lost power, lost Wi-Fi. It's just helping me know what's in my camera shot, okay? For instance, me or the whiteboard, all right? And it looks like the battery's starting to get low in the camera too. So let me try and do this fairly quickly. I'm going to give you the formula of the pickling solution. Okay? Now what you're going to have to do is you're going to have to set yourself up something that's acid resistant, whether it's a plastic barrel that you cut in half, or a plastic barrel that you can just, a plastic bucket that you can use that, it's got to be big enough for the bearing shell to be fully immersed. Okay? Hopefully you'll be able to see enough for this. Okay. It's going to be a solution, 1 part sulfuric, acid, okay, and 10 parts clean water. In other words, don't go out to your local stream and get yourself a bucket of creek water, okay? It's got to be clean so that this solution works well. Okay, now once you get this all mixed up, note to self and to you. If you're going to work with any acids, use your safety gear, face shield, rubber gloves, rubber apron. Do not splash any of this stuff on you. It will burn you badly. You might as well apply a oxyacetylene torch to your own skin, okay? If it gets into your face, you'll have a burned face. And you know, just to accentuate, it's going to hurt a lot. All right? So don't do any work with acids and you know, alkali solutions without protective gear on, okay? Remember, acid goes into water, not the other way around. If you watched my other video that had to do with wire rope sockets, I tried to really, you know, accentuate the point that you can't pour water into acid because it will boil and spit the acid back up at you, just like if you was to have a skillet of hot, you know, really hot oil, cooking oil on the stove, and you dripped some water in it. You know, if you've ever done that before, you see how violent a reaction that is. Same thing for acid. Always pour the acid into the water. You won't have the reaction. Pour water into acid, it's gonna almost like pouring molten metal over water. It'll blow out at you, okay, and you'll get hurt. All right. So please remember, always safety first. Okay. Let's say you've got this ready. You get yourself a bucket or a container, depending on the size of the bearings that you have, and you make enough of this to be able to fully immerse the bearing shell. Okay? Now, once you put it in there, 10 to 15 minutes soak time. Okay? That'll be plenty of time for the first layer, the outside layer of the material, to be eaten away. Okay? After that, you'll have very good, you know, fresh metal, clean metal with no oxides on the outside. Okay? Now, if this material is heated, and it never said how hot you had to do it, but if it's heated, I would presume not boiling hot. Okay, so you form you form steam at 212 degrees Fahrenheit. Okay, let's pretend I'm making up a temperature. Let's pretend it's going to be 150 degrees. If you have this at a heated up temperature, you don't have to have it in for 10 to 15 minutes anymore. If it's heated, 5 minutes. And if you're a shop that's got a lot of bearings to do, and you're trying to cut time on all of you know, all that process, heating up the pickling solution, it might be well worth the expense of heating it up. Okay, so that's pickling. Okay, now, good grief, where did I put my gosh darn eraser? I put it on the other table. I'll be right back. Yeah, there it is. Got it. Not planning ahead. Getting drifty in my old age. All right, so that's the pickling solution. All right. I can't stress enough safety gear for any acids or alkali solutions. Now, you got another way of doing it. You could dip it in a flux bath. Okay? It's almost like a pickling solution, but it's different from it. Okay, now the flux bath. Let's say it's like a pickling bath. It's a, you know, so you dip the bearing shell into it, and this is another old formula, really old formula. You take, it's going to be a saturated zinc solution. Okay, now how you make this zinc solution is that you get, it's going to be a large enough amount of liquid that you're going to be able to fully immerse the bearing shell in it, okay? Whatever that might be. Now, this is going to be acidic also, so it's got to be a, you know, plastic bucket or anything that's not going to be affected by acid. You take an X amount of hydrochloric acid, it's also known as muriatic acid, okay? Okay, the amount of hydrochloric acid or muriatic acid that you need is however much it'll cover the bearing shell, okay? Now, to make this zinc solution, you take that amount of acid in a container and you put zinc into it, you know, pure zinc. And I can't spell. Okay? What this is going to do is that the acid is going to dissolve the zinc. You let the acid continue to dissolve the zinc, and you'll know that this solution is finished when this acid can no longer dissolve zinc. All right, it's saturated, it's full, it can't, you know, no more of the zinc is going to be added to that mass. Okay. Once you got that done and no more zinc is being eaten up, you remove the zinc and now you have your zinc solution. You take that, yeah, this is easy enough. Once you've got that made, you get your bearing shells in one of the ears. That this is a bolt. The bolt goes through this. All right, you get yourself a wire and you just dip it into the zinc solution, and what you're supposed to do immediately thereafter is, if you have, you take it and pull it out, right? You shake off the excess material, all right? Just the stuff that's accumulated in there, that's on the surface, you shake it off back into the container, hopefully, and then you immediately take it over to a tin bath, and you slowly, carefully immerse it into the tin bath. All right, that has eaten, or is, you know, is eating the oxides away, and as it's doing it, you know, you bring it down into the, slowly but surely, into the tin bath, and it's been fluxed. That's a flux bath. Okay. Now, if you remember correctly, you can use that also to prepare the cables in wire rope sockets. Once you have broomed them out, you could dip it in that and you know, shake off the excess, then when it's, put it in the, whatever you're going to hang it on, but let the all the ends of the cables that are broomed up hang down and let it dry. That'll act real good as a flux for the zinc to apply itself to a bond to your steel ends. Okay. Let me check my list. Yep. And that is prepping the shell for the tinning. All right. That's several different ways. You don't have, obviously you don't do all of those things. You don't sandblast it and flux it and dip it in a flux solution and, all those. You can choose whichever one is more applicable to your situation in life. If you have something you can dip in, that would be, to me, that would be the best, all right? That way it's gotten into all the nooks and crannies, and, nature's doing it for you, okay? You don't have to worry about whether or not you rubbed on enough flux paste or dribbled on enough flux powder, that kind of thing. All right. Now, tinning the shell. Okay. I'll be back in a bit. I'm going to, just to keep from getting interrupted, I'm going to replace this battery, okay? Because last time I looked at it a few minutes ago, it was getting real low, all right? And I'll be back in a second. Okay, back to it. Yeah, the battery was pretty much almost dead. Okay, so let's see if we can readjust this. Oh, you're sideways almost there. All right, now we're going to get to the portion of it where you're going to be tinning. All right, now if you'll forgive me, I'm going to have to make a drawing. I am not a good 3D drawer with perspective drawer. So basically what I'm going to have to do is just do the best I can to draw a typical bearing. The bearing shell has an inside curvature and a wing, what we call wings, on the outside. It'll have a thickness thick enough so that this doesn't flex or distort under heat. And there's another wing. Okay? Now, let's see if I can get this out of here. That's just not part of it. Now that we're looking at it from the top, all right? Okay, and what you're gonna have to do is you're gonna have to tin everywhere. If we're looking at it from the top, that's the best way to do it, is that you're gonna have to put Babbitt in here, okay? You're gonna have to cast Babbitt in here. But if you, what you might not know is that you're also gonna have to cast Babbitt here. And here. See, I'm not even doing a good job. Okay. And here. Okay, so this would be the Babbitt you're casting. Let's see if I can do it a little bit better. If you were looking at it from the top, you wouldn't, after it's poured, you wouldn't see the top edge of the bearing shell any longer, because it'd be covered over by the Babbitt that's flowing over. Now, why is it we have to do these edges? Now, don't forget, it's not just the, well, let's see if I can, that was wrong. Doom, 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 cylindrical shape. All right. Wing, 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 wing. And the reason why you have your wings is because when these get put into the mechanism, they have to be bolted together, top and bottom. All right. And there's a shell of Babbitt. Let's say this is the inside shell right there. And this and this is basically the same thing. You need to not only have this overlap right here, but you need to have it overlap up here and overlap down here. Okay? And there's a logical reason for that. It's not just because somebody decided to do that for kicks and giggles. All the top curvature, the bottom curvature, and the two sides are going to have material poured, and you know, obviously this is going to be all poured at the same time. But all of these edges are going to have to be tinned so that the Babbitt, when it gets poured, can flow into there and bond with the bearing shell. Okay? I may not be a good person who draws a 3D perspective, but I can get the idea across. Now, why do we have to do that? I'll show you. It has to do with the differences of shrinkage. Okay, let's go ahead and do this. Let's see. Okay, there's that, there's that. Now here's the edge of the bearing shell. Okay. If you were to pour it with only from this edge to this edge, from top to bottom, once this solidified, remember this is, you have to bring this shell, the shell here, up to the proper pouring temperature so that the bearing material, the Babbitt, will bond with the tin, which has bonded with the shell. Okay, you have to bring both this material, this bearing shell, and the molten Babbitt material up to a certain temperature. Problem is, this material, the Babbitt, and this material, we'll say that it's steel bearing shell, cool down at different rates. Okay, and cool down at different rates. What they found was that if you allow this, you pour this just like this and you allow these to cool naturally, this edge right here pulls away from up here, because when this solidifies, this pulls, you know, as it's solidifying, like a bead on welding. Okay, if you do any welding, you know how when you pour or rather you weld a bead on something, and the something that you're welding might be this shape, you know that those two dimensions get wider from the solidification of the bead. It pulls on it from solidifying. Okay, the same thing happens here. Yeah, this has got material here and it'll start solidifying, but we've got a lot more material here that's drawing heat out. Okay, heat's going away, radiant heat, faster here, and therefore it's cooling faster here, from the bottom to the top and from the center out. Okay, so once this solidifies, and it solidifies this way, this gets pulled away from the bearing shell. If you have a gap in here, there's your defect. Okay, if there's a gap in there, it's going to vibrate. It's going to allow oil to get in there. In time, that vibration, the oil getting in there, will allow this to pull further and further and further away, all the way down until maybe that breaks off, or that breaks off, or it comes all the way down to here and breaks off, or when these are pulling, you know, coming out, maybe it doesn't break off, but maybe this comes in contact with the shaft and it starts melting that. Okay, heating this whole thing up and starts melting the Babbitt material. All right, numerous defects can happen. So it's very important that we don't just pour it to the edge right there. You've got to have it pour over here too, so that this portion of the whole deal is anchored and doesn't pull away. Okay? Let's see if I can make a better drawing, because I'm going to have to use the drawing to illustrate something else. Okay? Now, how is that looking? Still, maybe I'll be able to zoom in on it when I'm doing the editing, so it's easier for you guys to see. All right. You got the wing here. Got that. The wing. Boom. Coming around. Now, how are you going to do that? How are you going to make sure that it you know, when you tin this, don't forget you're tinning this edges all the way around too. But how are you going to make certain that the Babbitt is going to flow into there? After all, you don't want it to just, when you pour it into here, you don't want it to just flow out onto the ground. Okay? You just want it to go a little ways in there so that it anchors at that point. Well, what you do is you get some heat resistant material. What we used to use is asbestos, not paper, but we called it plate, but it's not really plate. It's only about, let's say 1/8 of an inch thick. It will, you know, you could substitute what I'm talking about with the material they use to work on boilers, okay? Because boilers can handle a lot of heat. But you get the material and the amount of area that you want this to be open, the rest of it, you make a slit of material that goes down. That's almost straight, I'll be danged. On the side, that represents the thickness. Jesus. Rotten drawing. Okay, to try and show it from the side here, you're going to leave a portion of this edge free of this material, but all the way down this entire length, you have to put that heat resistant material. You're making it into a gasket, in other words, okay? You not only do it on both sides, but on the bottom, let's say this is the bottom. Yeah. You're also going to make a curved portion of this heat resistant material. Now, if you ever made gaskets, you'll know what I'm talking about when it comes to making a gasket, okay? What we're trying to do here is we're not only trying to leave enough room in this exposed areas for the tinned surface to allow Babbitt to bond to it, you know, and mix with it, but we're also trying to put good enough gasketing material to prevent the molten material that we're pouring here. Let's say if we're pouring it in here, once it gets down to here, more often than not, if you have the smallest gap in here, if you have the smallest hole, it'll flow out. And all that really hot metal is going to be all over your floor, and you might be, you know, burning things up, okay? So, and then that's the hardest part about this job, I think, is just make absolutely certain that everything is sealed tight so that the molten material just stays right inside that form, which we will call a mandrel, and solidify where it has to solidify, not flow outwardly and all the material just flow down and you got nothing in here and everything starts all over again, because this is supposed to be absolutely clean in here before you try and pour Babbitt. After you pour it, you might come up to this point right here and all of a sudden, boom, this bursts, and then it flows downwardly, it leaks out, and you've got a thin layer of tin, which is adhered to the steel Babbitt shell, and a layer of really thin layer of Babbitt that's going to be oxidizing before you can ever try and pour that again, okay? So you got to seal all the seals. Now what we usually do, once you make your gaskets of both on the sides and on the bottom, once you get that done, and what we usually did is we just cut them out with a pair of scissors and then used white glue to glue them in place and hold them in place while we're trying to attach the whole thing to the mandrel. And what we do after that is, once you've clamped it to the mandrel, then you're going to have some type of mud or insulating caulk, C-A-U-L-K, caulk, to make a barrier, you know, to back up and fill in all those gaps and all those cracks and pinhole leaks that might be there. So okay, first let me give you the visualization of the mandrel. Now wait a minute, I might be jumping ahead. I have jumped ahead. I don't want to jump ahead. I don't want to jump ahead. What we're supposed to be talking about right now is we're trying to talk about how to tin the shell. Okay? that's why I got into all that, is because I wanted to show you or tell you that you didn't just tin the inside of the bearing shell, you also tin the outside perimeter, the periphery, okay, and why you had to do that. So now we're going to get back to the original subject of tinning the shell. You have, I mean, you don't necessarily want the entire shell with a layer of tin on it, okay? Though that, you know, if you was to dip it in a flux and take it over and dip it into the a tin bath, you know, a pot of molten tin, you're gonna have a nice layer of tin all the way around, which couldn't hurt, okay? Because you're gonna have that tin will have to deteriorate before, you know, the steel or cast iron will be exposed, and before that that cast iron and steel would start rusting. You know, wouldn't hurt. But let's say there's a rule against it. You know, there's a rule against it. Whatever your command might be, your company might be, there's a rule against it. What you can do is you can coat the areas that you don't want any tin to adhere to, especially if you're going to be dipping it into a tin bath. What you do is you're going to paint those areas with a barrier that can't be affected by the heat, okay? And that's going to be a red clay wash. The red clay wash is easy to make. Simple as can be, okay? You just get some of that red clay. Hell, if you live in Georgia, you've got to have bunches of deposits of red clay near you. I mean, there's a lot around there. But if you don't live there and you don't have any natural red clay deposits in your area, just go to your hobby store and get a chunk of that red modeling clay. Okay, just red clay. You take a container of clean water, and add red clay this readily dissolves in water. Okay, it you know, as with any material that's in nature, it's affected by water. So you take the red clay and you squish it up in your hands, and you put it, you know, maybe you'll sprinkle it in the water, but you just keep adding the red clay and stirring it until that water turns red. Now it doesn't have to be you know, just as soon as it turns red, okay, that's fine. That you've got enough red clay in the water to act as a wash at that time, okay? If you have some kind of reason why you need a bigger amount of thickness, you know, when it dries, it has to be, rather than just to be a barrier, a thin barrier between the two materials. If you want it thicker, you could add more red clay to it to make it more like a slurry, okay? And almost, you know, if you've ever worked with plaster of Paris, you know how thick that stuff can be. You could do the same thing here. Clay takes a lot of heat for clay to be burnt up by molten metal. And that, I mean, one of the reasons why I use bentonite, which is a clay, as my molding material for my sand. Okay? It takes a lot for that to burn up. So once this wash is painted on, you could dip it in. You dip it in the wash or whatever it is you're trying to coat, or if you're using it for a bearing shell, you could just get a paintbrush and dip it in the solution and paint it on. And anywhere that when it dries that there's a, you know, a red coating, that's, you know, you don't have to bother adding any more. All right, let it dry. If there's an area that it hasn't coated, you know, just like it just ran off, you know, just dip it on, add it to that. Okay, so you do this only to the areas that you don't want any of the molten metal to adhere to. All right. Now, you got to bring your bearing, your shell temperature, up to the melting temperature of tin, which in the United States would be 450 degrees Fahrenheit, and anywhere that that you use metric system, it would be 232 degrees Celsius. Okay, you bring that up, but you do ahead of time. You have, well, you have more than a couple, but in this instance, you have a couple of ways of applying tin to the bearing shell. One, you could have a tin pot that it melts the tin, keeps it at a molten temperature, and this is a much better way of doing, applying the tin to the bearing shell. The best way to totally immerse it, take it out, see if there's spots that haven't tinned, add a little bit of a little bit of the extra flux onto it, rub it in like with a clean wire brush, dip it, and just rinse and repeat until all the surfaces that you have to have tin on it has been tinned. Okay. Second, the one we usually did is we usually had a tin stick. Okay. Now, usually when you buy tin, you'll get it in ingots. Okay. Usually. What we wound up doing is that we would have a piece of angle iron, small angle iron. Yeah, that's not even understandable as being angle iron. Let's go ahead. We'll just do it this way: a side view of the angle iron and a top view of the angle iron. I can do that stuff much easier. Okay. What we usually wound up with is we would just get 1-inch angle iron, 3/4 inch angle iron. It didn't make any difference. You cut it to, we'll go with 8 inches, 9 inches. Cut that to 8 or 9 inches, and then on the ends of it, you block the open ends of the angle iron with pieces of plate, weld them in place, and then you pour molten zinc in there until you make a stick. You just turn it over, it'll fall out, and now you have, let's see if I can do this. That looks kind of like that if it's laying on its face. If this face were laying flat on a surface, that's about what it would look like. Now, when you take that, and it's only going to be about so wide, okay, at its widest. You take that and you hit it with a hammer on one end, okay, until you have something like this. You have the stick, and then you have some thin. This is thin tin, thin enough, let's say a piece of paper thin, a couple of threes of piece of paper thin, and then you know, if you've got to do a lot of them, you'll just continue to flatten this with a hammer, okay, and draw it out, so that, you know, it's harder for this surface to melt than it is from this surface to melt, because the heat is absorbed quite a bit more quickly than this here for it to melt. So you just rub it. Rub it on the inside surface This is very hot, remember. And you just go from one side to the other until the inside of this and the edges are coated with tin. Okay? So those are the two ways that we had done. There's more than another, there's other ways too. Like for instance, I have seen people with a spreadable tin. It's almost like a flux, but it's basically a tin coating that you can spread, and once you heat this up, then it melts and it spreads out, and it winds up coating the areas that you applied that to with a tin coating. And as long as the tin coating is pure enough and it doesn't have a bunch of other chemicals in there, the bearing will adhere or mix with that tin, which has bonded with the steel. Okay? That's the tin portion of it. And you want to make that little tin stick mold well ahead of time. It works easily. It's a very easy method, to just make the tin sticks, pound the end down thin, drawing it out, and then rubbing it on the inside of the curvature of the bearing. It's easy. It works well. Okay, but the tin bath, man, there's many a time I wish we had those, because it would have been even easier yet for that to happen. Any heat source to bring the bearing shell up to the 450 degrees, just like melting it out. You can use numerous heat sources to bring the shell up to the proper temperature, and like using a hawk burner, an oxyacetylene torch, and an oven. But here's the thing that I've got to emphasize. Care must be taken not to, when you're heating it up, not to put the flame on the inside. Because the machines that we use aren't perfect, whether it be a hawk burner, which sprays out atomized diesel fuel that's been lit off, or an oxyacetylene torch, which pushes out a very hot gas. Those two forms of flame don't necessarily 100% use up all the fuel. You're not just receiving the flame on whatever it is you're touching. Okay, in some cases, you're going to have unspent fuel being thrown into the curvature of the bearing shell, and that's going to act as a pollutant, a barrier, in other words, between the shell and the tin you're trying to apply. Okay, don't heat up the bearing shell on the inside, just work it on the outside. It's just as fast, and you're not going to be putting the possibility of putting unspent fuel on the inside curvature or the other portions that is supposed to be absolutely as clean as possible to allow the tin to adhere to it, or bond with it, I mean. Okay. Alright, and that much I've covered. There's nothing on that side. You apply the tin to the surface of the bearing shell where the Babbitt is to bond with the shell. Okay. And I showed it with the tin stick, and I showed it with the tin bath. Now, once that's done, you're going to, once you've tinned it, you're going to put on those gaskets, and you're going to, once you have the gaskets, glued into place, all right, that'll hold it in place, because while you're trying to, get the bearing and setting it onto the mandrel. Now here's what the mandrel looks like. I'll have to just do it from the top view and the side view again, because I am rubbish when it comes to 3D perspective. Top view, you're going to get a piece of pipe. Now this pipe is determined how big of a how big of a hole you want to form on the inside of that bearing. More often than not, we only had about a 1/2 inch thickness on the bearing shell, because they bring it down probably 3/8 or so. That's a machinist or rather a machinist repairman will have to chime in here and tell you how much on average the thickness of the bearing material was on the bearing shell. But we left plenty for them to work with, that's for sure. Okay, so this curvature, or rather this pipe that you're going to be cutting to the proper height, if let's say the bearing shell was, looking at it from the side, here's the wings. Okay, if the bearing shell was this high, you need to have that pipe that high. Okay, we don't want any of this bearing material, once you pour it in there, to flow into there. Okay, so we want it plenty tall to be able to have this act as a mold, form around which the bearing, the Babbitt material can form. Okay, so the size of this pipe and the height of the pipe when you're making this mandrel is totally dependent on the bearing shell itself. Okay, now once you've cut this, you're going to get a piece of plate and you're going to weld the pipe to the plate. Don't forget, the plate that you're welding it to has got to be big enough from here to here to allow the edge of the bearing shell, to be covered. All right, and I'll illustrate that in a second. You're going to have to put wings on the side here. All right, so that your regular, let's say this is the bearing shell, and there's the bolt down, the wings on the side. Okay, once you put it up against, I didn't do that, I didn't give you a gap in there. Imagine that there's a gap between this pipe and the inside shell here. Okay, that'll save a little bit of time on this drawing. Anyway, you're going to you can either clamp these ears to these walls, these wings right here, or you can drill holes. If you do a lot of them, if you're going to do a lot of that type, you might as well just drill the holes so that you can put a bolt through here and bolt it to those wings, drawing them up nice and tight. Okay, making it harder rather for the molten metal to flow out. All right. You can also, if you have two halves, you could use this other half. Now we have gone ahead and done this also. Have a big plate and then have another plate, and this is going to be, there's the 90, let's do it on the side view. And you have part of the pipe. We've had wings and the base plate and the pipe okay, like that. Instead of having a whole pipe and two halves, or rather a big plate so that both halves can be on here, more often than not, we would have this form where it's half a plate and rather half a pipe and half a plate, and you would just put the bearing shell on here and butt it up against this pipe, and the edges of the bearing shell would be butted up against the walls right here, and you can either clamp them with a C-clamp, or you can bolt them with nuts and bolted nuts and bolts. The advantage of having nuts and bolts is that when you're heating this all up, when this is all expanding, it's not going to, loosen the clamps and pop the clamps off. Okay, if you're just using C clamps, you're going to have it nice and tight when you have it put together originally, but the heating and cooling process of it might loosen it up. If you put bolts in there, that's not going to happen. It's going to stay there. It's going to be nice and solid, and you're not going to have to worry about it so much of it loosening up. Now, to make a bigger drawing of the same thing, and we have the pipe. Once you put the bearing shell on there, am I going to be able to do this good enough? Probably not. Okay, let's say this is the bearing shell. Boom. And down here like that. And this inside here is going to be a hidden line. So I can do this. To show that that form is still there. Here's one wing and one wing, and once this gets put together, let's say you have a bolt that goes through, right, both up here and down there. You're going to have to make a, you're going to have that gasketing material, okay, in there, but you can't trust that to be the thing that's going to stop this molten material from flowing out. So you're going to have to make up a mud, or use a high temperature refractory, material like the kind you would use in a to fill in cracks around a big boiler, a water boiler. And all along this mating surface on both sides, you fill it in with a mud. It's like you're caulking around a window. Okay? You do that along this edge, around the bottom, all the way around, and on the other side of this, you do it on that edge on the other side. Now, you're going to want to also make a dam up here. All right? So let's make it a little bit of wiggly, just to be not good. See, the thing is, once you pour the molten metal in here, this is all going to shrink. It's going to shrink against the inside of the bearing shell, and it's, well, hopefully it's, the preferred method that it shrink against the inside of the bearing shell here and not against the form. Okay, you want it to shrink against here so that it all just goes towards the form. And if it draws away from the form and it's not quite as full against the form, then no big deal, because that portion is going to be machined away. All right. If it does it the other way, perhaps it's going to pull away from the bearing shell. We don't want that. You know, we don't even want that possibility to exist. Okay. So, just making. I just had the thought to double check my batteries on the microphone. Is that still there? Yes, it's still there. Yay. Once I get started, I kind of forget to keep all these things checked out. And I've still got a picture over there. Yay. Okay, so a big mud all the way around the bottom, nice and thick. Really push it in there, because if you did the gasketing, if you glued the gasketing material on there nicely, that gasketing material, once you put this in place, is not going to move. Okay, but you are going to have a gap between the bearing shell and the mounting plate here. So you've got plenty of area in there. You can just totally flood that area with a nice hard amount of mud. You know, so your outside edge would be kind of like that. You want to have a nice thick bit of gasket caulking. You might call it caulking, but it's going to be a mud all the way around, so that the hydraulic pressure that's going to be the worst down here won't allow any place for the material to flow and empty this out. Now, as I was about to say before, you need a dam up here, because the top up here, if you don't give it some extra material, that's going to shrink down past this line, the edge of the bearing shell. And if it goes past that, okay, you're not going to have the entire surface of the bearing shell covered in zinc like it's supposed to be. All right, it'll be a failure at that point. Everything else is perfect. If this goes past down, you know, shrinks down past this edge, it's a failure. You need to have a amount up here. Let's see if I can make a bigger area. There's the bearing shell. You need to make a mud dam that goes all the way around, and is you know, slicked down good enough, like on the edges here, so that this is supported, you know, so that when you pour the molten metal, it won't just push it away. Okay. Once you fill it up all the way to the top of the dam, because once you pour it, and you know, you're going, there's a couple of things you're going to be doing. All right, you've secured it to the mandrel, you've mudded everything all around, and you've got a dam on top. Now you get a pot of bearing material, Babbitt, and you you bring it up to the pouring temperature. Let me double check the pouring temperature. Around 800 degrees Fahrenheit. That doesn't mean you heat this up to 800 degrees Fahrenheit. Okay? You're bringing the Babbitt up to 800 degrees Fahrenheit, so that, I mean, its melting temperature is considerably hotter than what this is. All right? So you bring that up to around 800 degrees Fahrenheit. And I was under the, my memory says that we brought it up to 900 something, but this is a good spot for you to look it up and see what the melting temperature of Babbitt is. And you're going to pour it into this. Now this, the mandrel, is going to be heated up to 300 degrees. Okay? Where did I put it? Oh, wait a minute. I got pouring temperature for Babbitt is 795. All right. Tin. Did I write that down? Okay, the melting temperature of tin is 450 degrees. Now what you're going to do is you're going to bring this up. Where did I put it? To 300 degrees Fahrenheit, so that this is ready. That once you pour the Babbitt in there, now Babbitt, don't forget, is grade 2 Babbitt is what you usually use. It's made up of 89% tin, 2% copper, and about 9% antimony, okay? The 89% tin, it's almost like you're pouring a tin bath into that. So it's hot enough that once it gets down here and starts coming up, it's hot enough that the tin coating that you have on the inside of the bearing shell is melted, and the bearing material, which is mostly tin, bonds with that tin coating as it goes up, okay? What we used to do, and I know we were wrong doing it, we would bring that up, the temperature of the mandrel and all that, up to melting temperature of tin. I noticed in those times that, you know, it sure does seem, with all this work that we've done to get rid of all the oxides and such, it sure does seem that we're making a lot of oxide by bringing the tin up to molten temperature, because I mean, it's not even paper thin. It's very thin, and you have just a small amount of mass in there being hit by a lot of heat. That accentuates the growth of, or rather accelerates the growth of oxides. Okay, I saw that the tin was turning, you know, not silver anymore. It was like a dark, almost like the color of lead. All right, so it was forming the oxides. I never understood it, but you know, you had to go by the instruction put out by NDT, non-destructive testing lab, and so that's the reason why. Okay, don't bring it up to tin, or rather the melting temperature of tin. You're going to make this ready to receive the Babbitt, and the Babbitt itself, once you introduce it into the gap in there, into the void, that's going to melt the tin and allow the Babbitt to adhere, or rather mix with the tin coating, which is bonded with the steel. Okay. So the mandrel is going to be 300 degrees Fahrenheit once you get it all ready. All right. The Babbitt temperature is going to be, or about 795 degrees Fahrenheit. Okay, you could make that an even 800. The Babbitt's not going to know that you've added 5 degrees. Okay. Now, you cross your fingers and you hope to heaven that it doesn't leak out when you pour it. What you have to do immediately after bringing up to the level of this mud, or rather of this lip dam, the dam. What you have to do immediately upon doing that is have ready a clean rod. Now it could be a clean welding rod. It doesn't have to be any bigger around than a brazing rod. Okay, if you ever see any of those, 1/8 of an inch in diameter, you don't want it to be whatever rod you choose. We would prefer, we preferred to have stainless steel, and we cleaned it up real good. We wiped them down real good with a degreaser. We didn't want to have anything in there to get in and be in the mix with the molten Babbitt, pardon me, and you know, put pollutions in with the molten Babbitt. You take a, oh, you must be running out. There you are. You take a rod, nice skinny rod, put it down to the bottom down here, and until it finishes solidifying all the way up here, you churn it. Put it in there, and you take, let's say this is the rod, you hit it on the bottom, and you go all the way around, back and forth, back and forth, and back and forth. And now what you're doing is you're doing two things. Number one, you're taking stock of where the solidification is taking place. Okay, everything poured perfectly. There's no leaks, no nothing. You have a massive Babbitt in there that's now got to cool. Okay, you take and you or somebody is going to be using a churning rod and churn all the way up around everywhere from side to side, and you're going to follow this material as it solidifies bottom to top. You continue to do it until it's solid all the way up to there. Once it's solid all the way up to there, you take a torch, or it could be a heat gun, for that matter, and you hit it and you let it flow until it's a smooth thing, because it's not going to be smooth when you're done. Even when it's almost all the way up to the top, you're still going to be hitting it, and so it's going to be like a layer of Babbitt with a bunch of it's going to be like a moonscape. It's not going to be smooth anymore. But so just to dress it up and make it look good, you just take a torch and you heat it up and let it flow nice and smooth. Okay, why are we churning? You're going to be keeping track of how it's coming up, solidifying. But because you poured that metal, that molten metal, from a, get this out of the way. Because you poured the pot of Babbitt down here from this edge of this pot all the way down to here, it's hitting, splashing, churning, and that means that it's also capturing air bubbles in there. Okay, with all that turbulence, it's capturing air bubbles. You want zero air in your material. You want it solid from bottom to top. So that's why you're churning it. When you're churning it, you're going to be forcing the air bubbles to the top while it's still molten. Okay, this is a heavy material. It's not like lead, okay, but it's pretty heavy. So the differences between specific gravity between the air and this material is great. So it'll readily go up. But if this heavy material traps air against the shell or somewhere in the melt, the little bubbles that are going to be formed by that turbulence is not going to be strong enough, not buoyant enough to force their way up to the top. That's what your churning rod is for. Okay, churn, churn, churn all the way up. Boom, you're done. Great. You take a torch or a heat gun and finish it off by melting it and letting it smooth out. That's the end of that. Now you take the bearing shell off of the mandrel. You take all the gasketing material off of it. You take all the mud that you shoved in the cracks. You take that off of it. Take a wire brush. In this case, it can be any wire brush because you're not really going to be touching anything that has to stay clean. And clean it up for the machinists, okay? Because you're going to have it, you're going to have a bunch of junk all over it that they don't necessarily want to have to work with. So you know, wire brush it off, clean it up, send it down to them in a nice, neat, a nice clean form, and they won't be cussing you out when you come down with it. Now, what's the machine shop got to do? Well, the machine shop, if you have access to a machine shop, and hopefully you'll have access to a machinist, what they have to do is they have to take the inside curvature of this whole thing. They have to machine that, or boring, you know, the boring, they'll use a boring tool, because once you get these bearing shells, let's see if I can draw a bearing shell again. Zoom around, boom, 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 and inside part of the shell. What you're going to be delivering to them is a bearing shell that's got a thickness of Babbitt material on it, and it's got the wings and all that. It's going to be basically the sides, top and bottom, has got Babbitt there. That really doesn't need to be there. Okay? So what they're going to have to do is, first, they're going to have to get rid of the material that was put there that prevented the edges from pulling away. The sides, they're going to have to, well, I think what they mainly did is they went and put it in a mill and milled it off. And then once they got to a certain level, they put it on a wear plate. Is that called a wear plate? Well, it was a cast iron plate that had all these cuts in it. And this only took off a tiny bit, like a thousandth at a time, you know, whenever they came back. Honing plate, I think they called it, honing plate. Anyway, they honed that down to where it was absolutely even with that face. Okay? And all right, ran out of battery. And we're almost done here anyway, okay? So I'm just going to hold here and hope like heck that it looks okay. Anyways, where am I? Oh, here it is. The bearing shell now has this excess material removed on the sides. They can now bolt these two halves together. Now, once they bolt those two halves together and machine them as a pair, they are paired up that way until they get mixed up later down the road. Okay? Because they want no, let's see if it's, say that we got the upper half. Okay, that's the bearing. They're bolted together. We want 0 oil seepage through this joint right here. Okay? So that's why they got to get these surfaces as paired up and flat as you possibly can. You want a tight joint right there. Then the tops and the bottoms, you know, once they get this put together, they can put it in the mill and mill away the top. They can mill away the bottom excess, and then all they have left at that point is this formed hole that we formed with the pipe, and then they can machine it, or you know, they can bore it to the appropriate size for that mechanism. So that's what once you pour that bearing and get it all cleaned up for the machine shop or the person who's going to machine it, well, it'll be done then. Okay. Once the machinist machines the whole thing and gets it ready for your mechanism, you can put it back in place and, you know, fill up that bearing. Not fill up. It's almost like you half full most of the time. You don't have to fill it all the way up, because once the oil starts heating up from friction, it just might back up and pour out the, you know, some of the upper portions of the bearing cracks and orifices and things like that. Okay, this is what we did in the Navy. Okay, this is how we did it. The basically, as a summary, I hope I'm not messing up your world too much right there. As a summary, what we did: received the bearings, melted out the old bearings, tinned the shell, made the you know, gaps in there by putting the gasketing material, which has to be a heat resistant material. Attached it to the mandrel as best we could, totally plugged up any and all gaps in there so that it would just pour and not leak out. Pour the molten metal. It will bring the temperature up. I mean, bring the mandrel up to the appropriate temperature. Get it preheated before the molten Babbitt gets there. Once that's ready, you get the pot of Babbitt. You bring it over. You pour it, and then as soon as it's poured, somebody with a churning you know, rod churns it until it's done solidifying. The top half is then torched off for nice and easy. You don't want it to heat it up so much that it pulls away from the bearing shell. You just want to barely heat it to allow the top to get smooth. You disconnect it from the mandrel, clean up the bearing shells, take it to whoever's going to machine it, and we never saw it again after that. I think in all my years of doing bearings, the only time we had to redo a bearing, or rather, you know, re-pour a bearing, is when the machine shop failed it from not having enough bond. Okay, we had to have a high percentage of bond, and that's what ticked me off the most. You know, as much effort as we put through it, even with machined dovetails in the bearing shell, you know, which acts as a physical anchor to keep the bearing material from coming loose, and holes. They bored holes. Oh, let's say that size, okay, in there, so that the Babbitt material can pour in there and act as an anchor. And that came from the old days, okay, because, you know, I don't think I read in any of the material they really understood that the chief, strongest way of making that bearing work the longest time is to bond the Babbitt material to the bearing shell by way of a tin interface. Okay, whenever any of that stuff started pulling away, they said, "Hey, let's go ahead and make an anchor," and then they would make an anchor. Okay, and that you know, worked in a way. They really didn't come loose. They didn't peel off anymore, other than the edges, around the edges. Once that stuff started coming in contact with the rotating shaft and heated up, and, you know, that would melt, and the heat would be transferred to the bearing shell, and that interface would melt, and it would pull away. You know, all kinds of bad stuff would happen. Okay, now, pardon me. As a molder, we did 3 jobs, in summary, to these videos. As a molder in the Navy, we, in the foundry, had 3 primary jobs. We did other little things, but nothing regular. We made castings to help all the ships in the Navy, you know, keep up with their missions. and the castings could have been mechanical, or the castings could have been decorative, like ship's plaques, which were given to people for re-enlisting. Okay, so it was important. If you knew you were going to get something nice to be able to hang on the wall, that might be just the one factor that'll push you over the edge and make you re-enlist. Okay. We also repaired wire rope sockets. Okay, lifting slings, in other words. So that was an interesting thing too. We had we had maybe one time we had one of those pull loose. Just I don't remember what the situation might have been, whether or not I wasn't there, or whether or not we didn't perform a step good enough, or anyway, or maybe because we never were on site whenever they did the weight testing, it might have also been that they added too much weight. Somebody figured how much weight that they were supposed to be lifting with. Maybe they put too much weight on that one, and it eventually pulled out. Okay, no idea what the truth is. I just remember we maybe had one time that we had to rework a wire rope socket. Then bearings, Babbitt bearings, which was the subject of this video. That was our third, written in stone function in the foundry. Okay, at the beginning of this series of videos, I promised that I was going to cover all 3 segments, and at the end of this one, I will have covered all 3 segments. From now on, what's my plans in the future? Well, if I ever get my hands on a bearing, or a pair of bearings, it's not never going to be very much. Size-wise, it's got to be small, because, well, I'm retired. I don't have a lot of money. Navy doesn't pay you a lot of money when you retire. It just forces you to become. You can become a spendthrift. You just be thrifty in your spending. And hey, I haven't gone without a meal. Obviously, I haven't gone without a meal, and I haven't had to sleep out in the rain. So because of my being in the Navy and staying for the 20 years, I have a good life, what I consider as a good life. Okay, I've been able to do almost everything that I've ever wanted to do, mainly because I don't want to own a boat. I don't want to have my own business. A lot of the things that people want, they have really big views of what they should be doing after they retire, and then they get themselves in trouble financially. Not me. I just became a worker bee after I got out, made enough money to be able to, by way of 401k, to pay off the house, and now, in my young/old age, I don't have to work anymore. What I am doing is I am passing along to you, my viewers, the stuff that I learned. Shut up. The stuff that I learned in the Navy. I did start saying what I was going to do in the future. Well, what I'm doing in the future is kind of vague. I will, if I get my hands on a small bearing, show you how that works. Show you step by step what we did in the Navy, how to pour a bearing. Okay, it's not the same way as a few of the other folks that I like to watch did. Just smoke the shaft and pour the molten material into the not even really heated bearing shell. There was a couple of times that I was listening, and boy, that bearing material was popping and burping out the front of the hole that they was pouring in, and that's only because they had moisture inside there. They didn't heat it up enough for that moisture to get out. Okay. And then there's some things that I do want to make, like for instance a bell. Now we're not going to make something the size of a ship's bell. The ship's bell of the tenders I was on, which was, you know, up forward just after the forecastle, the forwardmost portion of the ship. Those things, I think they weigh 250 pounds or something like that. I don't have enough brass and bronze around here to pour a you know, bronze bell that would weigh 5 pounds. Okay, but my wife, who loves drinking soda, is putting out a bunch of aluminum for me, and I'll be using aluminum as my casting medium. Okay. The next project I do have that I have in my mind is to show you how to pour, or rather ram up and pour a bell. You know, like a ding-a-ling-ling bell, you know. Not a big one, just a small one. But the techniques that I use to make a small one is the same thing, the same techniques that you'll be making for a larger one. Okay? The ones we usually made in the foundry were probably 6 inches tall, 8 inches tall, and the outside edge of the bell was 6 inches. Okay, these kind were meant to be on the quarterdecks to act as a signaling bell up there. It was fun to make. Sometimes, you know, frustrating because the what formed the inside curvature of the bell would fall out, but it was still fun to make. So this is the end of this video, and so now I've got stuff to put away. I hope I was able to give you enough information to be able to do bearings the proper way. Please remember, safety first. Whenever you're working with molten metal or you're working with acids, safety gear on at all times. Okay? And with that, I'll say see you later. Arrivederci. And for those of you who were Navy molders, pattern makers, what is it? What is it? That's right. Liberty Call.